Hey everyone, today I want to make a YouTube video explaining the intuition behind the line integral. So, in order to explain this, I would actually like to use the example of gravity. So, gravity is all around us. For instance, if I were to drop this marker, it would actually experience an acceleration and drop to the floor. But how do we plot gravity? One way to look at gravity is this. Let's say I make a graph of x, y, and z. You can view gravity as a force of little arrows pointing downward. And it is this force that causes the acceleration of anything toward the Earth. In this case, the arrows are not only equally spaced, but they also have the same magnitude, so they have the same force. And they also have the same direction. Notice that they're all pointing down toward the Earth. This is to symbolize that everything that is in free fall will drop toward the Earth. For instance, this marker won't fly up into the air. It would only fly up if the vector was pointing upward. And then I would like to talk about the work-energy theorem. So let me just erase this for a second. And let me bring up a popular physics problem. Let's say we have a box with a mass here. Let's say we have a height. And let's say we have a little ramp. This ramp has no friction. And so, in this problem, let's say this height is 0, but it goes up to 5 meters in this case. Now, for this box, let's say its initial velocity is 0. And we want to find out the final velocity here. In this case, what we don't want to do is sum up all the forces along this ramp, like as a line integral, to solve for the final velocity. Instead, what we do is we pick the easiest and most convenient path possible, which is this. So, what we do is we basically say the change in the potential energy plus the change in the kinetic energy equals to 0. So here, I'm going to do just the mass of the box times gravity. Gravity is just acceleration vector pointing downward here. So this is the final height. Minus the initial height. So in this case, the reason why I'm doing subtraction is when you move something upward toward the Earth, it will gain potential energy. And so we're trying to find out the difference between the potential energy at these 2 points. And here I'm going to do 1/2 mv squared of the final and the initial velocities. This, in this case, is 0. HF is 0, so this expression is 0. This box doesn't move at first, so this expression is also 0. And based on these two, we can find the final velocity right here. Now, why are we able to do this? Why can we just pick this instead of having to do a line integral through this ramp? The reason is the gravity field G is conservative. I'm going to try to talk about conservativeness through the line integral, and I will do 2 more examples, so don't worry about this if it doesn't make sense right now. So in this case, we know that G is conservative. Now, let me bring up the first example. In the first example, I'm going to do a box. And in this time, I'm going to draw a box moving through a loop. So in this case, pretend that I'm moving a box, or any object in this case. It could be this. And so I'm going to move this in a loop. I'm going to start here. I'm going to move up here. I'm going to move to the left, to the right, I mean. And then I'm going to move it down and back to the left, back to where it started. In this case, all 4 lengths are h. And also, I'm going to split this into 4 segments. So, this is S1. The marker's terrible. Anyway, this is S1, this is S2, this is S3, and this is S4. I also need to bring up the definition of work in physics. So, in physics, the definition of work is equal to force times distance. If the vectors aren't in the same direction, I'm going to use F as the vector for force. So the brackets just mean the absolute magnitude. D is the vector for distance, and I'm going to take the cosine of the angle theta between them. And so here is what it looks like. This is your vector D, this is your angle theta, and this is your vector F. And so we're just trying to, in physics, when we talk about work, we're only concerned about the portion of the force that is in the direction of your distance that you're moving. So we're not concerned about the other direction of force that goes upward. That is not related to the direction of the vector D. Now, once I brought this up, let me try to find the total work of this. If I were to erase this real quick, this mark is terrible. Anyway, the total work is equal to the work on S1, segment 1, plus work on S2, plus work on S3 and S4. This is similar to how you can break a line integral up into multiple segments and sum them up. So, in this case, we have a gravity vector. Let's say we have the gravity vector G that's pointing downward. So this is the gravity force. And here's our H. So, let me just symbolize it with the force right now. So, here we have a force. I'm going to represent the height as a vector here. For the first one, since we're lifting the box up, or we're lifting this object upward, we're actually going, and the h vector is pointing up. So our force is in the same direction as h here. And so the angle between the two forces is 0 because they're not like this. For S2, again, we're moving a force, but this time it's this way. However, I'm sorry. The h vector actually doesn't apply here. So we're still applying a force, but we're only concerned about the direction h vector that we're going upward. So the vector h here only points upward. But the force that we're applying goes this way here. So it goes, our force goes upward here, to the right, downward, and to the left. So in this case, the vector h and this force vector are 90 degrees apart. So I'm just going to do cosine of 90 degrees. Here, I'm going to do, it's going downward this time. The h vector is still pointing up, but the force vector is pointing downward. So gravity is pulling it down. So I'm going to say that the angle between them was 180 degrees. And now, in the final case, S4 is similar to S2 here. Only this time, the force vector is pointing to the left, but they are still 90 degrees apart. Now, cosine of 90 is 0, so these two cancel out. Cosine of 180 actually turns it into a minus sign. So, in this case, I'm going to replace the force with the magnitude of the gravity field here. Because what happens is, if we're lifting this thing up against gravity, we actually need to apply an equal force, but in the opposite direction, in order to make it move upward. Here is the minus sign from cosine of 180 degrees, whereas cosine of 0 is 1. So the expression remains unchanged. These two will also cancel out, and so our final result is 0. So in this case, the work done is technically 0. It sounds a little weird, but if you're moving something in a gravity field back to where it started, you technically haven't done any work. Just like if you took the line integral in a conservative vector field, any conservative vector field, not just a gravity field, it's also going to be 0. Next, I'm going to explain this using a full line integral explanation. So I'm not just going to do this. So I'm going to move from this example into the next one. All right, so let's return back to the plot of the gravity field here. Just like before. So this is our y, our x, and here's our z. I'm not going to draw too many lines just for simplicity here. But let's say I draw a loop through here. Actually, let me make this bigger. That way it's easier to see. So, let's say you have this. In this case, let's say we're moving in a counterclockwise direction. So let's say we start here, and we're going to move in a clockwise direction back to the original starting point here. So let's start here. Our dr vector, dry markers, anyway. Our vector points upward. Our gravity vector, g, points downward. That means they're 180 degrees apart. They're 180 degrees apart. In this case, this is our dr vector here. And this is our capital G vector pointing downward. Let's call this theta here, since we don't know the angle. In this case, our dr vector is pointing down here. So it's actually in the same direction as the gravity field vector, capital G. And then the angle here is 0. And finally, here's our dr vector here. And we don't know what this angle is, so I'm just going to call it theta prime. Theta prime, from what it looks like, due to the symmetry of the gravitational field, since it's all pointing downward, it is actually the same angle as, it is the complement of the angle theta. So, when we actually do this, let's say we take work as a line integral through this expression. The closed loop here actually just means we're moving in a full circle back to where we started. But this is basically the same thing as a regular line integral over this curve. All right, now, I'm just going to talk about these 4 components and I'm going to ignore the rest. I know this isn't a very rigorous explanation, but I just want to give some intuition behind what's actually going on here. So again, they are the 2 vectors here. We're moving upward, but the gravity field vector is pulling downward. So they're 180 degrees apart. We will take cosine of 180 degrees. Now, to this point, let's call it cosine of theta. For this point, they're in the same direction. So, it will be cosine of 0 degrees. And lastly, we're going to substitute in theta prime for 180 minus theta. Everything good so far? All right. Now, in this case, cosine of theta is actually equal to the minus of cosine of 180 degrees. So, as you can tell here, this is actually going to be the negative of this value. So these two are going to cancel out. And in this case, we already seen earlier that the cosine of 180 degrees is a -1, whereas this is a +1. So these two will cancel out too. So the work done is still 0 here. And now, this actually applies for all conservative vector fields, not just the gravity field itself. So, anytime that you take a line integral in a closed loop through a conservative vector field without singularities, that means when you go back to the same point, the final result will be 0. So in this case, in chapter 16.5, you'll talk about using curl to test whether a field is conservative or not. In this case, the curl of the gravity field is 0 because everything is pointing downward. There is no rotation at a particular point in the vector field. So since this is 0, the vector field G is conservative. And just to clarify here, work is a scalar value that we do. So work is a scalar value in physics. It's the energy that we expend in doing something. Let me erase all this, and I just want to do a final comparison because I want to compare the physics to the math expressions. So let me rewrite it again. Work as a line integral. In this case, I'm talking about a closed loop integral. Is equal to the loop of the line integral. And we've already seen that it equals to 0. But to actually evaluate the line integral, what's going to happen is you're going to find a potential function. Now, remember how we talked about the mass sliding down the ramp expression earlier? Anytime that you lift something up, it's going to gain potential energy. And so this function, u of x, y, and z, is going to tell you the potential energy based on where the object is located. Now, in the previous example, we moved the object around like this. Forgive my horrible drawing, but we started right here, we moved upward, and we moved back. There we go, to where we started. So, I'm just going to say this is x naught, y naught, and z naught. In this case, when we first started here, the object did have some potential energy. It may have been. It may have been sitting on the ground like this, or it may have been in the air like this. But, and here is our point. Here's our initial point. And as we move it, we eventually go back to where we started. And so, this is where we began, and this is where we ended. However, even if these values are non-zero, because we ended where we started, the difference between them is zero. And so, although the potential energy of the object may not be zero here, the total work done, the total scalar value, is still zero here. And just to clarify, for potential energy for the Earth, our x and y actually don't matter. It's actually only our z. So if I have this marker right here and this marker right here, let's say the z-axis is our height, and the x and y are located right here. If these two markers are at the same height, they have the same potential energy, even though they are different x and y values, but they are at the same z values. But in this case, since we're working in 3 dimensions, I just included x and y in here because we're working in a 3-dimensional space. And now, here's our physics right here. For our math, in chapter 16.3, you've learned that whenever you take a line integral, you get a scalar value. In this case, I'm going to do it from a point ABC in space to D, E, and F. So we're basically moving the point from a point here, ABC, to a point here, D, E, F. Now, here's our vector field, general vector field F. And here's our dr vector. So we're moving this through the space. Now, to evaluate the line integral, we can use the fundamental theorem of calculus. And so we can plug in D, E, and F minus, I should use another one. Let's call this G. Let's call this G, and here's A, B, and C. And we basically find a difference between these 2 points here. Now, if you notice this scalar value right here is like work. Work is also a scalar value. Our force, our vector field F, is like our gravity field G. And in 16.3, we talked about the concept of a potential function. In this case, our potential function little f is just like our potential energy function U. And so, by evaluating the potential function f at these 2 points in space, we can find out our scalar value through evaluating the line integral. I hope this helps, and I hope this helps you understand the concepts behind 16.3, including the one on the potential function f. I hope this helps, and good luck in Math 1D.